Hamel? Massey is here. Bishop? Bragg? Here. Caudill? Chestnut? Colwood? Here. Erlinson? Gerard? Green? Kennedy? Leonard? Mohammed Boyd is here. Small?
Here.
Sullivan? Here. And Swisler. All right, so we're going to continue our discussion. If I'm not mistaken, the last thing we looked at was I think we did the first two examples, right? Okay, so this is the last one that we need to do now. So let me do the usual copy and pasting. So this question says, label of a stock bottle of aqueous ammonia indicates that the solution is 28.0% ammonia by mass and has a density of 0.898 grams per mil. So the question is asking you to calculate the molarity of this solution. Now, of course, we know what molarity is. Molarity, by definition, is equal to moles of solute divided by liters of solution. All right. So if you can find the moles present in 1 liter, then basically you would have determined the molarity. So what I'm going to do is assume that we're starting off with 1 liter of solution, right? And basically what we want to get from that eventually is the moles of the solid, right? So I'm going to start off with 1 liter of solution. And then I'm going to convert that to milliliters. So 1 liter of solution down here and 1,000 milliliters of solution above. And then, based on the information provided, I can find the mass because the question gave us the density in grams per mil. So I'm going to express this as a conversion factor here, where I'm going to put 0.898 grams of the solution above, and below I'm going to put 1 milliliter of the solution below, right? So this would go with that, that would go with that. So up to this point, we would have determined the mass of the solution. Now, according to the question, 28% of that solution by mass will be the actual ammonia. So I can represent that here in this conversion factor, where I can put, or I would put 28.0 grams of ammonia above as numerator and 100 grams of the solution below as a denominator, all right? So this unit will cancel with that unit. And then that's it. All we need to do now is find the mass as a result of what we have here. So that would be 1,000 times 0.898 times 28. Oh, divided by 100. Hold on. Oh, we're not finished yet. There's one more step. And the next step is to find the moles. That's what we're trying to find. So let me take out the equal sign here. And so to find the moles, of course, we have to go to the periodic table, and if I remember correctly, the molar mass of ammonia is 17.03 grams of ammonia. And that would be equal to 1 mole of ammonia, which will go up here as numerator. Okay, so now we can do the number crunching. So as I was saying, 1,000 times 0.898 times 28 divided by 100 divided by 17.03. And this doesn't look right. Okay, so the answer I got is 14, when rounded off to 368, 14.8 M or moles of ammonia. So therefore, the final answer is 14.8 moles per liter, or 14.8 M, same thing, right? So that would be the final answer. Okay? All right, any questions about this? Yes, sir.
Is there a question like that?
Let's see, see if I can, so I'm not sure if a question exactly like what we just did is here, but there are some questions that deal with polarity, so let's start by looking at number 14. Number 14 says, how many grams of potassium carbonate are needed to make 200 milliliters of 2.5 m solution? Right? So the way I would go about doing this one is I would start off with the 200 milliliters of solution. All right, of the solution. And I will convert that to liters. 1 liter of solution for 1,000 mils of solution. And then I will multiply that by the molarity, which would be expressed as 2.5 moles of the potassium carbonate over 1 liter of the solution. All right, so far, these are the units I would cancel out. But remember now the question is asking for the mass in grams. So we have to find the molar mass of potassium carbonate. So I'm going to go to my trusty molar mass calculator. So for potassium carbonate, K2CO3, molar mass is 138.21. So I'm going to put that one 138.21 grams of K2CO3 over 1 mole of K2CO3. And then we do the number crunching. So let me go back to here. So let's see what this gives. 200 divided by 1,000 times 2.5 times 138.21. And according to my calculation, this works out to be equal to, rounded out to 3 sig figs, 69.1 grams of K2CO3. All right, so in practice, and those of you enrolled in my lab, we did an experiment yesterday which deals with making solutions and so on. And therefore, you should be familiar with this, what I'm about to say. So in practice, what you do is you weigh, in this case, 69.1 grams of your potassium carbonate. You'll put it in your 200 ml volumetric flask. You add some water to it, not much, not all the way up to the top. And then you stopper it, shake it up, make sure that all the potassium carbonate dissolves. And then you continue to add water until you get to a final volume of 200 mils. And then you stopper it again, shake it up, and then.
Why is it 360 not 2?
Because, oh, you know what? You're right. It should be 2. Because of the 2.5. Thank you. Yeah, it should be 2. So that should be 69 grams. All right. So that's basically what that is done. All right. Any questions about this? Any questions? Any questions? Okay, so let me hear what you have to suggest concerning number 15. It says in number 15, how many liters of a 4M solution can be made using 100 grams of lithium bromide? So how would you do that problem? They gave you the molarity and they gave you the mass. And remember, just to remind you, molarity is equal to moles per liter, right? So what the question is asking for is this. So how would you go about solving this problem? Hmm? Liters would be equal to moles but divided by molarity. Right? So we have the molarity already, which is the 4M. How do we find the moles?
Add up the atomic mass of everything divided
Oh,
by
right.
100 grams.
So you need to know what the formula of lithium bromide is. What's the formula of lithium bromide? LiBr, exactly. So you go to the periodic table, or if you're lazy like me, you go to your molecular weight calculator, and you put in the formula of LiR. Of course, you guys don't have the opportunity to do that. So anyway, so basically, okay, so the molar mass is 86.85 grams per mole, right? So how do we calculate the moles based on that number? They gave us the mass, which is 100 grams, right? So how do we calculate the moles based on that? And then, what do we multiply this by? So 1 molar mass.
1 mole.
And then down here, 86.85 grams. And then we divide that by the molarity, which is 4 moles per liter. So the gram units will cancel out, the mole units will cancel out. So the final units you're going to end up with is liter unit. So 100 divided by 86.85, and then we divide that by 4. And according to my calculation, when rounded off to 1 sig fig, that's going to be 0.3 liters. That's it. Right? Question about it. Any questions out there in Zoom? No. Is it okay if we declare this? Exactly. All right, so let me scroll down to the next question, 16. It says, what is the concentration of a 450 ml solution that contains 200 grams of iron 2 chloride? So presumably the concentration they're asking for would be in moles per liter. So how would you tackle this problem? Again, remember, molarity is equal to moles per liter, moles over liters, right? So how do we get the moles in this case? They gave us the mass, right? And they gave us the name of the compound, which is iron 2 chloride. So we need to figure out what the formula is. So what's the formula for iron 2 chloride?
FeCO2.
FeCl2. Oops. FeCl2, all right? So we need to find the molar mass of iron 2 chloride. FeCl2. And that's 126.75. So the molar mass here is 126.75 grams per mole, right? Okay, so going back to the question. So to get the molarity, we divide the moles. So how do we get the moles? Now that we have the molar mass here, and they gave us the grams, how do we get the moles?
200 grams.
200 grams multiplied by,
1 mole on top,
right?
126.75, the denominator.
Okay. So that will give you the moles, right? Because the gram units will cancel out here and here. Then we divide by the volume in liters. Now they gave us the volume as being 450 mils. So we need to convert that to liters by doing what? What goes up top here and what goes below here?
1 liter, 1,000
1
milliliters.
liter up top, 1,000 mils below. So in terms of units canceling, this will cancel with that. So therefore, your final units will be moles per liter. So it's all a matter now of doing the math. 200 divided by 126.75 divided by, that's basically 0.45. So according to my calculations, the answer would have to be rounded off to 3/6. So in this case, the answer is 3.51. 3.51 moles per liter. All right? Okay, any questions about that one? Any questions? All right, okay. All right, so number 17 says, how many grams of ammonium sulfate are needed to make a 0.25 liter solution at a concentration of 6.0 m? All right, so let me hear what you guys have to say about this one. Exactly, but you have to take another step. I mean, what you said is correct in terms of the initial step, so 6.0 moles per liter multiplied by the volume. Right? So this will go with that. But there's one other step that you need to take. I'm sorry? And how will you do that? You convert the moles to grams, you're correct. So how will you do that? What will you multiply by in order for you to convert the mole value to grams? You need the molar mass, which means that you need to know what the formula of ammonium sulfate is, right? So what's the formula of ammonium sulfate? Well, that's why I gave you those charts with the list of ions. Remember that there were 3 pages which gives you the ions and their charges, and therefore based on that, you can determine the formula for pretty much any ionic compound.
NH4, 2.
Okay,
SO4,
hold on a minute, NH4,
parentheses 2, SO4.
yeah, exactly. So that's the formula for ammonium sulfate, and again, I'm going to use the molecular mass calculator, so NH4, 2, SO4. And let's see what that gives. 132.14. So that will go right here. 132.14 grams per mole. And that's pretty much set up. Let's see what the result is. 6 times 0.25 times 132.14, and that gives 198. Well, rounded off 2 sig figs, that would be 198. Okay, so I would have to express this in scientific notation. 2.0 times 10 to the 2, and the units here will be grams, because they have to round this off to 2 sig figs. So the mole units will cancel out, and you'll be left with your answer expressed in grams, right? Okay, any question about this one? Any questions? Okay, how about the last one here, number 18? What is the concentration of a solution at a volume of 2.50 liters and contain 660 grams of calcium phosphate? So that's easy, that's similar to what we just did earlier. So to calculate the molarity in this case, we need the moles. And to get the moles, we start off with the 660 grams of the calcium phosphate, and we have to multiply by 1 mole over the molar mass of calcium phosphate. So Ca3 PO4 2, that's the formula for calcium phosphate. So that's 310.18, and that would go down here, 310.18 grams. So when we do that calculation, we're going to end up with the moles, and then we divide that by the volume in liters. And they gave us the volume exactly in liters. They gave us 2.50 liters. That's it. So 660 divided by 310 divided by 2.5. And according to my calculations, when rounded off to 3 sig figs, the answer I got is 0.852 N. And that's how that is done. All right? Okay, so that's the last question. Now, I just realized this morning that there's some more questions I need to add for this chapter. So I'll make sure, and I think I might post it online, or maybe I'll just bring it to class and post it as well, so that we can do a couple of those. Because we need to do some questions dealing with stereo, with we call it solution stoichiometry, and also dilutions, right, which we're going to talk about shortly. Okay, so yes, sir.
So when you wrote the answer with capital M, that's the same as the most.
Exactly, yeah, most believe that M.
It doesn't matter if you write capital M.
Same thing. Yes, ma'am.
I know it's like kind of.
Okay, number 4. Only for you. But maybe not only for you, maybe your students and that's good. Number 4, what is, oh, okay, number 4 is a combustion question, so. Here it's first. Okay, so number 4 says after combustion with excess oxygen, a 12.501 gram of a petroleum compound produces 38.196 grams of carbon dioxide and 18.752 grams of water. A previous analysis determined that the compound does not contain oxygen. That's very important. Because what that tells you that there's only carbon and hydrogen present, right? So the question is asking for you to determine the empirical formula for the compound. So the way I go about doing this is that I will start off with the 38.196 grams of the carbon dioxide. And I would find out the mass in grams of carbon in it. So the first thing I'll do is I'll find the moles. 1 mole of carbon dioxide above, 44.01 grams of carbon dioxide below. This goes with that, right? And then, in terms of the compound itself, 1 mole of carbon dioxide will contain 1 mole of carbon, right? And then I will stop there. So 38.196 divided by 44.41. And according to my calculation, this works out to be equal to 0.8679 moles of carbon. And then I'll do something similar with the water, 18.752 grams of water. I'll convert that to moles, so that means I'll multiply by 1 mole of H2O divided by 18.02 grams of H2O. So that cancels with that. And then, and this is where I told you guys that students tend to make a mistake. Here, you're going to put 1 mole of H2O here. And above, you're going to put 2 moles of hydrogen. Remember, for every 1 molecule of water, there are 2 atoms of hydrogen, right? So every 1 mole of H2O, 2 moles of hydrogen. And then we do this calculation here. 18.752 divided by 18.02 times 2. So according to my calculation, this works out to be equal to 2.081 mole. So this is the moles of carbon, this is the moles of hydrogen, right? So the next step is I would well, I like to do this in a tabular form. Yes, sir.
Second one is carbon.
Hydrogen, I'm sorry, yeah, you're right. Hydrogen. Yes, ma'am.
So if there's 2 moles of hydrogen per 1 mole of oxygen.
No, 1 mole of water. Right, exactly. These 2 right here, exactly. Okay, so let me just gonna write these numbers here just to remind me of them. 6, 7, 9. Carbon 2.081 mole. Hydrogen, because I need space. So let me erase. Here. So I'm gonna start with my table. We at the top, I'm gonna have carbon and hydrogen. And these would be the mole values. 0.8679 moles. 2.081 moles. And then I would divide by the lower mole value. So divided by 0.8679 moles. This would give 1, and this would be 2.081 moles divided by 0.8679 moles. So let me see what that gives. 2.081 divided by 0.8679. And I got, now this would have to be rounded off to 468, 2.398. So the question now is, because this number here is too far from the nearest integer, right? So the question is, what do we multiply this right through by in order to convert this number into an integer? So in this case here, this one is one of those numbers that I can't tell directly. I'll have to do some trial and error kind of thing. I know it's not 2, I know it can't multiply by 3. Not 4. Let me try 6. So 2.398. Oh, that does work.
I got 12 on here.
What's that?
I have 12.
12? What do you mean?
C5H12.
Oh, you mean, so what do you multiply to get 12?
By 5.
Oh, okay, by
The
5.
2.4 by 5 times 5.
Okay, yeah, okay, yeah, you're right, because if you multiply right here by 5. This becomes, what I got is 11.99, which is approximately 12. And this will be 5, of course. So therefore, the empirical formula would be C5H12. Yes, sir.
And why multiply by 5?
Well, you have to choose a number, an integer, that when you multiply this number by it, it becomes an integer. Or very close to an integer. So as he correctly said, 5 would be that number, because when I multiply that number by 5, I got 11.99, which is almost square, right? So that's where you get that. So therefore, the answer, the empirical formula is C5H12.
Can you do a molecular one?
Which one?
Next one's molecular.
Okay, let me here it is. And scroll down. Okay, so in this case, it's the same type of problem. Again, it contains only carbon and hydrogen. So let me just go through the steps quickly. So I would first start off with, now in this case, they gave us 5.86 milligrams of carbon dioxide. Now in this case, what I would do is first convert to grams. So 1 gram of CO2, 1,000 grams of CO2 down here, and then I'll convert to moles. So 1 mole of CO2 above, and the molar mass of carbon dioxide, which is 44.01 grams of CO2 below, and then 1 mole of CO2 down here, 1 mole of carbon above. So let's see what I get. So that's 5.86 times, or divided by 1,000, divided by 44.01. And according to my calculation, this works out to be 1.33 times 10 to the minus 4 moles carbon. And then in the case of water, it's 1.37 milligrams of H2O, milligrams of H2O. And then we have, again, converting to grams, so 1 gram of H2O above, 1,000 milligrams of H2O below. And then here we have the molar mass, so 1 mole of H2O above, and CO2, not CO2, H2O would have a molar mass of 18.02 grams. And then here, again, make sure that it's 2 moles of hydrogen for every 1 mole of water, right? Very important. Okay, so let's see what this gives. 1.37 divided by 1,000 divided by 18.02 times 2. So according to my calculation, this works out to be 1.52 times 10 to the minus 4 moles of hydrogen. So I'm going to set up my table, carbon, hydrogen. So as far as the moles are concerned, the carbon would be 1.33 times 10 to the minus 4 moles. And for the hydrogen, it's 1.52 times 10 to the minus 4 moles. And then we divide by the lower of the two, which is the 1.33 times 10 to the minus 4. So this is going to give 1, and this is going to give 1.14. And if I remember correctly for this one, again, because this number is too far from the nearest integer, if I remember correctly for this one, and I think somebody asked me about this one already. I think you multiply by 7 right through. Let's see, 1.14 times 7. Yeah. So when you do that, you're going to get 7 here and 8 here, right? And then that means that the empirical formula is equal to C7H8, right? Now the question is asking for the molecular formula, right? and they gave us the molar mass. So what we need to do now is find the empirical mass. So, C7H8 calculate 92.14 is the empirical mass. (92.14 grams per mole is the empirical mass, and the molar mass is 92. So this is approximately equal to the molar mass. So what does that mean? That means that the molecular formula is the same, C7H8, right? That's it. Yes, sir. Okay, what are you talking about?
It's the,
You mean here?
yeah, right there, what's that?
Excuse me, 1.33 times 10 to the minus 4. You look at these two numbers here, and you divide right through by the lower of those two numbers, which is the 1.33 times 10 to the minus 4. Okay, so the empirical formula we just got is C7H8, right? And then based on that, I calculated the empirical mass, right? And the empirical mass is 92.14, and the molar mass is 92. So they're about the same, right? If they were different, then what you'd have to do is find the integral factor. The integral factor would be the molar mass divided by the empirical mass. In this case, because they're the same, the integral factor is 1. But if it was something else, let's say for example, if this was 2, then what you'd have to do is multiply this by 2 and this by 2. See what I'm saying? So the answer would be C14H16 in that case, right? Okay. Any other questions about this particular? Yes, ma'am.
So when you're multiplying by an integer to get like, coming from what is like the exact range, like how far can it be?
So if I'm understanding your question, how far is the number from the nearest integer in order for you to not multiply by?
Yes.
Okay. If I remember correctly, I think it's usually if it's 0.1 or 0.2 or something like that. But you know, if it's point something away from the nearest integer, then you should consider multiplying right through by a certain number to convert that into an integer. Right? Okay, any other question? Any other question about this? Okay, so let me clear this. And let me go to the PowerPoint because we need to discuss dilutions. And for those of you enrolled in my lab, you have already been introduced to this concept, right? So this should be a bit of a review for you. But basically, as I said to my lab class, on Tuesday, dilution is very important, practice pretty much everywhere chemicals are handled. And you know, that's true for teaching labs or even the most advanced research facilities, because very often what you'll find is that you may end up in a situation where you're doing an experiment which requires a solution of a particular concentration, but what you have in your stockroom is a solution of the same substance, but it's more concentrated. So therefore, you have to know to what extent to dilute that solution to get the required concentration, right? The key thing you need to remember when it comes to diluting any solution is that when you add solvents to your solution, you're changing the volume, of course, but you will not change the amount of solute present in the solution, right? So whatever the amount of solute that you had before in the more concentrated solution will be the same as in a more dilute solution after dilution, right? So as a result of that, okay, so here's an example. We have a solution initially of iodine, where we had the molarity is 0.050 m, where it was 0.0050 moles of iodine dissolved in 0.10 liter of solution. And then this person decided to add more solvent to it, more water, and basically the volume is increased from 0.10 liters to 0.50 liters. But you'll notice that the moles of the solute does not change. So since the volume changed, that means that the resulting molarity would be less, right? And because the volume increased by a factor of 5, that means that the concentration is reduced by a factor of 5. So basically, upon dilution, or even before or after dilution, we can say that the concentration, the concentration times the volume is equal to a constant. All right? And the constant would be the amount of solute present because that doesn't change, right? So basically, it's this product that we exploit in order to determine the extent to which we're going to dilute our solution. So this is the equation that is used. As I said before, the moles of solute doesn't change. So therefore, the molarity times the volume is equal to the mole, which is constant. So therefore, we can say that the concentration of the concentrated solution times its volume will be equal to the concentration of the dilute solution times its volume. The way I prefer to express it is C1 V1 is equal to C2 V2. All right. And whenever you're using this equation, it doesn't matter what the units are for concentration or for volume, as long as you're the same on both sides, right? So the molarity units for C1 must be the same for C2, and the same is true for the volume units. Volume units could be liters, milliliters, gallons, whatever, right? But the units must be the same, right? And that's important because you could be given a question where V1 is given in milliliters, V2 is given in liters. That means you have to do some conversion before you plug the numbers into the equation, and then you solve it. All right. Okay, so here is an example. And again, you guys in the lab would have some experience with this. We did not use this pipette here. That's a glass pipette. But instead you guys use the granite cylinder, but the principles are still the same. The pipettes are actually more accurate in terms of measuring, but we were not concerned about that in the lab that we did on Tuesday. Anyway, so this question says, how many mils of a 2.00 M copper 2 sulfate stock solution are needed to prepare a 0.250 liter of a 0.400 M copper 2 sulfate solution? So the equation that you'll be using is, as I said before, C1 V1 is equal to C2 V2. Now, what the question is asking for is the volume of the more concentrated solution, right? Because the question gave us C1, they gave us C2, and also V2, right? So to solve for V1, that would be equal to C2 V2 over C1. And then all we have to do is plug the numbers in, 2.0, no, I'm sorry, not 2.0, 0.400 M times 0.250 liters divided by 2.00 M, and that would give the answer. So 0.4 times 0.25 divided by 2. So according to my calculation, this would be equal to 0.050 liters. So basically what you'd have to do is measure 0.050 liters of the more concentrated solution, and then you add water until the final volume of the solution is 0.250 liters. And that's what's being demonstrated in these pictures. So the first picture on the left is your 2.0 M copper 2 sulfate in a bottle. And what this person did was to use this pipette to measure 50 mils of that solution, right? And then that solution is transferred into this, which is called the volumetric flask. And basically, as I said to the class on Tuesday, the flask is made very accurately, right? They come in different sizes. If I remember correctly, the smallest one I've seen is like a 10 mil. And then the largest one I've seen is, I think, 2 liters, all right? So basically, and also, you can't see from here, but these flasks are, have on the stem etched a mark, right? And that mark would represent the volume of the solution in the flask, right? So in this particular case, the flask is a 250 milliliter flask. So when you add liquid up to that mark, then you know that you have 250, and I would say to 2 decimal places, 0.00 milliliters of liquid, right? So what this person did was transferred 50 mils of the solution here into the flask, right? And then they just simply add water until the water level, the meniscus gets up to that mark. And then they stopper it and shake it up just to make sure that the solution is homogeneous. And that's basically how that dilution is achieved, all right? And this is very, very routine, very routine practice, as I said before, in labs all over. In fact, if you plan to work in a lab of any kind or any kind dealing with chemicals, then you'll be expected to know how to do this, all right? Okay, any questions about this? Any questions? Any questions? Questions? Okay, now let's talk about solutions in chemical reaction. I think this will be the last thing we're going to discuss. Actually, no, it's left time. So let's talk about this question right here. It says, okay, so in this topic, we're dealing with molarity as it relates to what we learned earlier with respect to stoichiometry, right? So just to remind you, stoichiometry basically deals with quantitative relationships between substances in a chemical reaction. And of course, we have to, in solving stoichiometric problems, we have to work with balance equations, right? So you're going to see a combination of what we learned earlier and also what we just learned with respect to solutions and molarity and so on, right? So of course, you have to remember that when it comes to molarity, the relationship between the moles of solute and the volume of solution is moles of solute divided by liters of solution, and that gives you the molarity, right? So this here is a scheme that we met before, right? Where if you're given grams of a substance A involved in a reaction, and you want to find the grams of substance B involved in the same reaction, you have to first convert to moles. Then we use the mole ratio between the two based on the coefficients in the balance equation to get the moles of the substance B, and then we multiply the moles of substance B by the molar mass to get the mass of the substance, right? So a lot of the stoichiometric type problems involve, in some way, in whole or part, this approach, all right? Now, in some cases, you need to determine the grams of substance A based on previous information. So for example, you may be given the volume and density of the substance, then you can find the mass of the substance, all right? And the same is true down here when it comes to substance B, all right? Because you could be asked how to determine, let's say, the mass of, not mass, the volume of substance B, and you got the mass, you can multiply or divide the mass by the density, and that will give you the volume, all right? Now, when solutions are involved, then you have to take into account the molarity. So for example, you may know the concentration of substance A, right? In which case, to get the moles of substance A, you'd have to multiply the molarity by the volume in liters, and that gives you the moles, and then you can do the rest of the calculation. In the case of substance B, you could be asked for the volume, in which case you need to know the molarity, or you could be asked for the molarity, in which case you need to know the volume. So those are just, possible problems of different types that you could encounter when it comes to determining, different things when it comes to solutions involved in reaction. Now, unfortunately, I don't have an example on this PowerPoint slide, so what I'm going to do is go to our good friends at Google and see if I can get a question dealing with solution stoichiometry. So maybe an example or two we can work out to see. Let me see. I don't want any answer key, that's too boring. Okay, here we go. Okay. So this one is a typical solution stoichiometry problem, the first one. We can probably, let me just check what the others here. So that's number one, number two. Okay, these are pretty good questions, right? In fact, what I'm going to do, I'm going to save this, and I'll probably post it later. in Canvas so that you guys can have a look at it. I'll probably tackle the first. All right, I'll go for the first four. So the first question says, how many grams of calcium phosphate can be produced from the reaction of 2.50 liters of a 0.250 m calcium chloride solution and excess phosphoric acid? All right, so first thing we need to do is what?
What's the equation?
Right, a balanced equation, which means that we need to figure out what the formulas are for these substances are. So, what's the formula for calcium chloride? CaCl2. What's the formula for phosphoric acid? Phosphoric acid.
H3PO4.
H3PO4. What's the formula for calcium phosphate?
Cu3,
Ca.
Ca3, sorry,
Yeah, Ca3.
parentheses, PO4,
Mhm.
2.
Okay, very good. And then hydrochloric acid.
HCl.
HCl, very good. So now we have to balance it. So how do we go about balancing this equation? No, let me upload this into Canvas now. Okay, where shall I put it? I'll put it under, no. Did I put it on the assignments? I'll put it on the assignment. And then I'm going to, okay, hold on. Wait a minute here. I'm going to say as solution stoichiometry problems. So, I'm going to put it in the assignment section. So. Okay, so it's now there, so you can try the other problems. Yes, it's right here at this point, so no, it's fine, all right. So let me get back to that, all right. So yes, we need to balance this equation. So how do we go about balancing this equation? I'm sorry, repeat that. 3, 2, 1, 6. That's correct. Yes. Okay. So we have to do that first before we can do anything else. All right. So the question gives you the volume and the molarity of the calcium chloride. And the question is asking for the grams of calcium phosphate. So how would you go about solving this problem? Let me hear some ideas. You have 3 calcium chlorides on this side here. Well, you have 3 calciums here and 3 calciums, so that's the reason why the calciums are balanced.
Was it C?
Oh, yes, I'm sorry, it should be 3, my bad. Please forgive my poor handwriting. So this should be 3. Still messed up. A, 3. All right, so how shall we start the calculations of? What's the first step?
Moles of calcium.
Okay, so how will you, that's good, but how will you do that? You're right, you're gonna find the moles of calcium chloride, right? So how will you go about doing that? Well, you have the molarity and you have the volume, right? So, what's that? Exactly, so you're gonna do 2.50 liters of calcium chloride. And you're going to multiply that by the molarity, which can be expressed as 0.250 moles of calcium chloride for every 1 liter of calcium chloride. So that this goes with that. So now we would have calculated up to this point the moles of calcium chloride. So what's the next step? Convert, nope, not quite. You're going to do some gram conversion later on, but before you do that, there's something you need to do. Can anybody tell me what that is? What goes here?
Moles of calcium chloride at the bottom,
Okay,
over calcium phosphate.
okay, okay. So the moles of calcium chloride below and above would be moles of what?
Calcium phosphate.
Calcium phosphate, Ca3PO4 2, all right? So what would be the numbers here and here? Nope. Oh, wait a minute. Yeah, you're right. My bad. 1 here and 3 here. And that comes from the coefficients in the Banach equation, right? Okay. So this would go with that. What's the next step? We have to convert the moles of calcium phosphate to grams. So what goes below here would be 1 mole of Ca3PO4, 2, and above you need to calculate the molar mass. Again, I'm going to go to my calculator. Okay, so that's it. 310.18 would be placed here. 310.18 grams of Ca3PO4 2, right? So now we need to do the number crunching. So 2.5 multiplied by 0.25 was that divided by 3 times 310.18. And according to my calculation, and please tell me if I'm on the right track here, but according to my calculation, we round it out to 3 sig figs. The answer I got is 64.6 grams of calcium phosphate. All right. That's what I got. Please tell me if I'm wrong, but that's what I got. All right, any questions about it? Any questions? Questions? Okay, let me see what you have to say about the second question. The second question is asking, it gives you a balanced equation, which you need to check to make sure, let me check and make sure it's balanced. 14 hydrogens, 15 hydrogens. Okay, wait a minute. Oh, yes, 14 hydrogens. And then 1,4 times 3 plus 3 oxygens, that's 45 on one side. 2, 3, 6, 6, 6 is 36, 36, and 2, 38, plus 7, 45, okay. And then 6 coppers on both sides. Okay, so the equation is balanced. Yeah, make sure you check on, that the equation is balanced. First time I'm seeing these questions, so that's what I'm checking. Because I've seen some errors before, so very important for you to check. All right, so now that we're sure that the equation is balanced, the question says, how many milliliters of a 1.5 m nitric acid solution is required to react with 100 grams of cuprous oxide, which is the same thing as copper 1 oxide, which is this right here, right? Okay, so any ideas? How would we tackle this problem?
100 grams.
Okay.
Oxide.
100.0 grams of Cu2O. What will you do with that?
1 mole on top.
Mm-hmm.
You have to find the molar mass of it.
Okay. So CU2O, and that gives you 143.09. What reason? Oh, it's the wrong thing, look at it. All right, so 143.09 grams of CU2O, all right? Okay, next step. What goes here? Because up to now, we have determined the mole, right?
Is it 143.09?
Yeah, that's the molar mass of the copper two oxide. Okay, so what's the next step? Okay, what ratio are we looking at here now? The moles of nitric acid and. Oh, so 40 moles of HNO3 above. And down here. 3 moles of CU2O. Then what? Now remember what the question is asking for. How many
Milliliter.
milliliters up to this point you would have determined the moles of nitric acid? The question is asking for how many milliliters of the nitric acid. So the question is, what would be the next conversion factor that you're going to put there, which would finally allow you to calculate the, well, actually there are 2 conversion factors, but should lead to the answer in milliliters. You're going to need one conversion factor and then another one after that.
Would it be, the 1.5 moles in a 1 liter?
Okay, so how would you set that up here? What goes up top, what goes below?
1 liter on top.
Exactly, 1 liter of nitric acid above. And
1.5 mole.
1.50 moles of HNO3 below. So that this goes with that. So up to this point, you'd have calculated the liters of nitric acid, and then there's one final step.
Then
And
you
that
gotta
is to
go
convert to,
liters to milliliters.
right, so how would you do that? What goes up top, what goes below? 1,000 milliliters of nitric acid above. And 1 liter of nitric acid below. Right? So that this will go with that, and then we do the number crunching. So 100 divided by 143.09 times 14 divided by 3 divided by 1.5 times 1,000. And according to my calculations, please correct me if I'm wrong, but I got 2,174 liters of HNO3.
Milliliters.
I mean milliliters, sorry, yeah, you're right. Of HNO3. Right, that's what I got. All right? Any questions about this? Any questions? So, is it okay for me to clear this? All right, let me do that. Let's go down. Okay, so number 3 says 60.5 mils of nitric acid are required to react with 25.0 mils of a 1.00 m barium hydroxide solution. Now it gives you the equation, but it says it's unbalanced, so you have to balance it. And then the question is asking for you to find the molarity of the nitric acid. All right. So first task is to balance this equation. So how would you go about balancing it? No,
Oh, that's 3, 4 here.
so how would you go about balancing it? The two in front of the HNO3? Is that it? Not so sure about that. Because from the look of things, the hydrogens are not balanced on both sides. There you go. Now it's done, all right, okay. So that's the first step. So now we need to do the math part of it. The question is asking for us to find the molarity of the nitric acid, right? They gave us the volume of the nitric acid. So if they gave you the volume of the nitric acid, the only other thing you need to find is the moles to find the molarity. So how would we find the moles? And the answer lies in this information right here. The fact that you have a 25 mils of a 1.00 m barium hydroxide solution. So the way I would go about solving this is I will start off with the 25.0 mils of the barium hydroxide solution. I will convert that to liters. So I'll multiply this by 1 liter over, 1 liter of barium hydroxide. Down here, I'm going to put 1,000 mils of barium hydroxide. And then I multiply this by the molarity, which is 1.00 moles of barium hydroxide over 1 liter of barium hydroxide. So in terms of the units that will cancel out, this will cancel out with that, this will cancel out with that. So up to this point, you'll be left with the moles of barium hydroxide, right? The next conversion factor would express the mole ratio based on the balanced equation between barium hydroxide and the nitric acid, right? So the mole ratio, as you can see here, is 2 to 1. So I'm going to put 2 moles of HNO3 above and 1 mole of barium hydroxide below, right? So all of what we have done here, let me cancel out this with this here. All that we have done here will lead us to determine the moles of nitric acid, right? But remember I said that the question is asking for what? The molarity of nitric acid. So whatever you get here, you have to divide that by the volume. What's the volume? 60.5 mils, which must be converted to liters, right? So that means you have to multiply this by 1 liter over 1,000 mils. And this is all for the nitric acid. So let me put HNO3 here, HNO3 here, and HNO3 here. So this goes with that, right? And that's it. That's the setup. So let's see what the answer is. 25 divided by 1,000 times 1 times 2, and then divide by 60.5 divided by 1,000. And the answer I got is rounded off to 368, 0.0605. And the units here will be moles per liter. Let me do this again just to make sure my calculation is correct. Oh, no, this is wrong. Okay. Let's do it again. And the answer I got this time is 0.826 moles per liter. Please confirm this just to make sure I'm doing this right.
Speed,
60.5. I got it from here. Okay, any other questions?
I came out way different.
The final answer? All right, let me do this again. I could be wrong. Anybody else got something different from that? That's what I got. Did it twice. I don't know. All right, okay, I think I'll stop here. What I suggest you do is try these problems on your own. Right, I posted it in Canvas. And that's pretty much it for chapter 3. I need to add some more questions to the assignment itself because I need to include some solutions, stoichiometry and dilution problems in that. So look out for that. Yes, sir.
these, so you said it's fine.
Yeah, I just published it, right? I just pulled them from Google and I think these are very good practice questions for solutions, stoichiometry. Huh? No, I mean, just for you to, you know, get some practice. I'll let you know, because I need to add something to it first. And then, when I add it, I'll let you know when it's due.
Then we have to take our test next week, correct?
Yes, so the test next week, Thursday, next week this time, we'll cover chapters 1 and 2, right? I won't include 3, all right? So,
That's in the testing center, we're taking it.
no, here, right. The testing center is only for hybrid classes and online classes, not for face-to-face. Yes,
See,
Like, the code is on the meeting idea, but I'm very sorry.
password, there's no password, you just go to, you just go to modules. Have you tried it?
I did.
Okay. Okay, let me get it.
I entered the meeting ID, it asked me for my.
That should be, no, because see, I recorded videos on YouTube. There we go to modules. And these are the classes so far. And then you click on, you know, that should bring it over. Click on that, and you go.
Thank you.
Take care. Right.
Thank you, I was looking elsewhere.
Oh, okay, yeah, so that's where all my classes are, including today's. Yes, ma'am.
If I were to do this on a test, is there any more fun?
Well,
I wrote the answer.
yeah, no, it should include you this year. That's the only issue.
Do you have to rewrite that?
Mhm.
Noted.
Yeah. Yes, ma'am. Okay, for you guys out there in Zoom, I'm signing off.
Oh, I had one more question.
Oh, yes, sir.
So you said we're testing next week, like in class. Is it on
Yes.
Tuesday and Thursday, or is it like Tuesday?
Thursday.
Or like is it just
Thursday.
one day we're testing?
Yes, sir. Next week, Thursday.
Just Thursday? I'm sorry?
Yeah, just mhm.
Okay, so we're testing next week, Thursday, correct?
Yep. Normal
Okay.
class Tuesday and then the test on Thursday. And the test
Okay.
will be basically chapters 1 and 2.
1 and 2. All right. Perfect. Okay.
All right?
All right. You have a good one.
Yeah, you too. Take care.